Hey, kid, you want a toy? How about a bike?
No.
A video game?
No!
Well, okay. You pick a toy.
I want... log! Boy, oh boy!
Yes, log. All kids love log.
One rolls downstairs, older and pairs, rolls over your neighbor's dog. What's great for a snack and fits on your back? It's log, log, log. It's log, log. It's big, it's heavy, it's wood. It's log, log. It's better than bad, it's good. Everyone wants a log. You're gonna love it, log. Come on and get your log. Everyone needs a log.
Log from Blammo.
Good evening, Bearcats. This is section 3.2 logarithmic functions and their graphs, and this is part day 2. First, I want to give a nice shout out to Naomi for the really entertaining, fun little, I guess, cartoon before the movie, you could say, and kind of a blast from the past about our log video. So that was kind of fun. All right, let's take a look now at, we're going to continue logarithms, and we're going to talk about natural logarithms, which have to do with that natural base e that we talked about when we talked about the base e exponentials. All right, just take a little excerpt from our book here, and we're noticing a couple of things that by looking back at the graphs of natural exponential functions, we noticed that f of x equaled e to the x power was a one-to-one property, and so it had an inverse. The inverse function is called a natural logarithm function and is denoted by a special symbol ln x and is read as natural log of x or ln of x. Note that the natural logarithm is written without a base and that the base is understood to be b. Okay, so basically what this is if we have a logarithm with base e, so ln e, sorry, not ln e, ln x, ln is our natural log. We could rewrite that as log base ex, which again could be rewritten as log of approximately 2.7 something x. And that would all be basically the same thing. Of course, ln x would be the most accurate, or ln e we could use also in the calculator. Notice that the natural logarithm function is modeled by this log base ex, or ln x, and that x has to be greater than 0. All right, let's move on. A couple more things from our textbook. The definition implies that natural logarithm functions and the natural exponential functions are inverses of each other, and they are. So it doesn't imply that they are. So natural log functions and natural exponential functions are inverses of each other. So every logarithm equation can be written as an equivalent exponential form. So we can switch back and forth form to form very easily. And we've practiced that some yesterday. We'll continue to practice that more. And every exponential equation written as log form. That is, y equals ln x and x equals e to the y are equivalent equations. Because the function f of x equals e to the x and g of x equals ln x are inverse functions, their graphs are reflections over the y equals x line. You can notice that here in this reflective property, or in this figure 3.18 right here. So notice that they reflect. This is your exponential, and this is your log. It's a natural log, ln, but they reflect over that y equals x line. All right, next let's just take a look at some properties. These are all basically the same properties as we had for our regular logarithms. We have ln1 equals 0. Because remember, this is like base e, so e to the 0 power would be 1. ln e equals 1 because base e to the first power would equal e. E to the x equals x, basically because e ln x equals x, Now, I think what you need to look at when you have this inverse property is know that the e and the l, or the ln and the e, kind of cancel each other out. So your value is x. And finally, ln x equals ln y if the y is equal to the x. The x is equal to the y. And that's a one-to-one property. We'll use that a little bit more later. All right, let's use these properties to try to simplify these expressions. The first one we have is ln 1 over e. I think I'd move that e upstairs, and I would get ln e to the negative 1. All right, just remember that our ln and e are inverses of each other. They kind of undo each other and become 1. That's like 1 times negative 1, and our final answer here would just be 1, or negative 1. Let's take a look at the next one. This is e ln to the 5. Again, e and ln sort of undo one another, and therefore we would be equal to 5 would be my answer. Part C. We have ln 1 over 3. We learned about that a while ago. ln 1 over 3. All right, let's take a look at ln 1 for a minute. ln 1 can be written as e to some power equals 1. What would that be? That would have to be 0. So that would end up being 0 over 3 equals 0. 0 over 3 equals 0. And finally, we'll do D, and I apologize for running out of room here. So we have 2 ln e. All right, for 2 ln e, then we're going to have that equal to something. All right, so remember, ln and e again become 1, and we have 2 times 1 equals 2. And so 2 would be our answer. All right, those are not too hard. That's just switching from form to form. The last little section we're going to do is we're going to talk about the domains of the logarithm function. Domains and ranges are going to be really important for us. So let's take a look, and we're going to think about transformations. I'm going to go ahead and draw a little graph here. We're going to talk about transformations. So this x minus 2 would really mean I would go to the right 2. But I need my parent points first. Since there's no base there, we're going to assume all of these is base 10. And so we would have base 10 would be the same as the exponential 10 to the x power. We're going to create a t-table for our base function only. This is a base function. So we'll have our x and our y, our base function. Now, if we want a logarithm function, we're going to have to switch out our x and y. Normally, traditionally, we would write the x values as negative 2, negative 1, 0, 1, and 2. Because we're flip-flopping them, all of a sudden our y values become the negative 2, negative 1, 0, 1, and 2. And we will plug those values into this x, which is the same as plugging it into this x in a natural log, but you can't do the computations without a calculator, but you can here. And you'll find what now are the y values, are the x values of the log function. So we take a negative 2, we put it as 1 over 10 to the positive 2, which would be 1 over 100, or 200. Next one is negative 1, that would be 10 to the negative 1 is 1 over 10. All right, for 0, anything to the 0 power would be 0. For 1, we plug in 1, we get 10 to the first would be 10, and 10 squared, of course, would be 1,000. All right, that gives us some base points. The base points, the key point, of course, is at 0, and that should be. So our key point is 1, 0, and that's true for almost all logs, unless they've been shifted to the right or the left, when that may happen to us in just a minute. But first we're just getting the base points on. So our base point is there. We have 1/10, negative 1, and we have 1 at negative 1/200 and negative 2. And then we go to the other pairs, and we have 0. Sorry, we have a 10 So way out here in our graph, and at 10 we have a 1. So it really, really flattens out. That tells me enough that this function goes on forever. I'm going to draw in what sort of the sketch might look like. Alright, so now what we want to do is we want to shift this graph to the right 2. So we take every point and go to the right 2. This is your key point. So take it 1, 2. It was already at 1. So now it's at 3. And then all of a sudden, if you've shifted to the right 2, 1, 2, this line becomes your asymptote. So this point is got to get closer to that. So you've got 1/4 and then 1/8. And then going the other way, you've moved each of these points. This point was at 10, 1, and now it's going to be moved over to the right 2. So it'll be at 10 or 12. Alright, and so if you draw in the real graph now, it's a little better. That's your real graph. Alright, the domain. The domain is going to be all x values greater than the asymptote, so greater than 2. So all x values greater than 2. So you could put 2, comma, infinity, don't include 2. Infinity's never included because you can't reach, of course, infinity. Alright, let's take a look at B and C here. So let's get to B. Again, you're going to have a similar situation. We're going to rewrite this one. This is probably a really, really good one. Let me just get a new page to write on. So our next problem is going to be g of x equals ln 2 minus x. I would rewrite this. I would write this as g of x equals ln. I'd move the x in the front, so that's a negative x plus 2. I would probably factor out the x next, so I would probably write g of x equals ln, and then I'd probably have a negative and a parentheses, and I'd have x minus 2. X minus 2. Alright, let's see if we can graph. What are our transformations? One, we have a transformation with the x. We have two things going on. We have this negative sign, which will mean reflection, and we have the minus 2, so this is going to be, oh, what happened to my reflection? Sorry. Reflection, and we're going to go to the right 2. So we're going to go to the right 2, but we're going to reflect next. Alright, so let's try that on our graph. Again, back to those same key parent points. This would be base E again, and so ln, you're going to go at 1, 0 as a point, and then you know at the next one you're really, really close, and then you're even really closer, and then you go up pretty far, and then you kind of go up a little more even further. So that's pretty much the parent functions of a natural logarithm. And now what we want to do is we want to take it to the right 2. So 1, this was my original. And now we're going to take it to 3, 4. So to the right 2. And then we've got to reflect. And since this is with x, it's going to happen vertically or horizontally over the y-axis. So we took this to the right 2, and now we have to, and now we have to reflect. So this would be at 3, and we have to reflect over, puts us at negative 3. Alright, so that was this point. Let's take a look at this point. So we would have 1, 2, and we have to write 3. Okay, our asymptote was negative 1, and now our asymptote was y x equals 0. And so our new asymptote, think about this, our new asymptote would be anything that made this positive, and then not 1 itself. So we would have two would be a critical value. 2 would make it 0. Alright, so we take this key point and we would move it to the right 2. So 1, 2. And then we've got to reflect over that axis. So it'd be way back over here. Okay, then we can take another point and go right 1, 2, and reflect way over here. And we could take this 1, 2, and then reflect back over here. And we take this 1, 2, and reflect back over here. So your graph is going to look something like this. Not very pretty. There should be a better curve in here, by the way. Should be a better curve. Alright, but there you get the idea of our graph. So the domain here would be all numbers less than negative 2, or less than negative 2, less than negative 2. So was it negative 2? I am so sorry. I'm having some technical difficulties with my video, and the screen keeps going black on me. I don't know what you can see or not. So I'm going to start this problem over. I'm not sure if you can see it, but I can't see it right now. So I'm going to just put an X through here. I don't know if you can even see that. And I'm going to start over on this one problem. So let's take a look at this one more time. I didn't like the way that looked, and then it went black on me, so I can't see it. All right, so again, we're going to start with g of x equals ln 2 minus x. Okay, so we're going to go ahead and graph here. I hope you can see this. My screen is kind of acting up. And because this is x, 2 minus x, 2 would make it 0, so we're going to move over to the right 2. That would be my asymptote. We know the negative here is going to be a reflection of the x, horizontal reflection, so we're going to reflect over our axis once we move. And so our graph is going to end up looking sort of like this. We'll talk about this a little bit more tomorrow. All right, and I'm going to give you one more situation. We're talking about the domain. The domain is really what we're trying to focus on. Our domain in this case would be everything less than 2. Less than 2, so that would be actually from negative infinity to 2. And not including 2, so we would not have a hard bracket. All right. I think that is good for tonight. We are going to do a few problems tomorrow. Let me look at your homework set for tomorrow, so you'll already have that. And then we will finish up and start our worksheet. All right, so your homework, or your classwork, I should say, for tomorrow will be on page 237 again. We were there today. And we will be doing problems 49 through 55 odd. We'll do 65 through 71 odd, 79 through 83 odd, and finally 89 through 92 all, and then problems 99 and 100. Okay, these first 3 sets are really, really, really important, so make sure you fully understand them. This will be a little more challenging for you, and we can talk about that tomorrow. All right, Bearcats, have a good evening, and I'll see you tomorrow. Go Bearcats!